Thanks a lot, both for the introduction and for the invitation. So I don't know how you usually run it. If you want to, you can just, if you have questions in the meantime, just unmute and ask. That's probably the easiest, so if anything's unclear. So it's Linköping University, Swedish, yeah. So let's look a bit at what agenda I have planned for today. So first we'll look really introducing the problem. What is the art gallery problem and what are variants that have been looked at? Then we look at one specific type of variant, which are K-transmitters, and we'll see a bit what guards can do then. We'll move briefly into introducing what mobile guards are. So that's what we usually call the watchman route problem. And then we'll go to a recent work from me and a colleague, which are K-transmitter watchman routes, and then we'll go into a few details there, and then I give a general outlook on these problems. So I don't know how familiar you are with these problems, so I'll try to go a bit into the basic definitions. So for the art gallery problem, we're given some kind of polygon, and we want to know how many guards do we need to monitor it. And so that, as the name indicates, was at some point motivated by Victor Klee about guarding actually art galleries. Just one thing, I see that someone is putting something in the chat. I don't think I can open
it's
it.
A question for me. Sorry.
Okay, good. Then I don't have to open it. And so the question there was, you're having an art gallery and you want to be able to see all the exhibits. And then what you look at is a ground plan of the art gallery and how many guards do we need. And so, of course, normally a guard looks something like that. So it's a person. For us, it's point shaped. So you can essentially think of the head of that guard as a point, and from that we can see. So what does seeing mean? In the original version, it's mimicking human vision. So we can't look around corners or can't look through walls. That is, we can see another point if the direct line connection is fully contained in the polygon. And so in this case, this red guard could see all these dark red points, and that's what we call the visibility polygon of a guard. And what we can see here, at least this one guard cannot see the complete polygon. So for this specific polygon, if we place, for example, a second one here, then we actually see everything. So then we could ask ourselves, is that the best we can do? Could we have placed them better? And here we can actually also give a proof that we can't do better. And this is what we then use, for example, our so-called witnesses. So if you look at this turquoise and the violet point and their visibility polygons, so the dark turquoise and dark violet thing, they are disjoint. So I know that I can't use one guard that both will see the turquoise and the violet point. So I need at least two. And so in general, these witnesses are points in the polygon who have pairwise disjoint visibility polygons. And the maximum number of witnesses will always give me a lower bound on the minimum number of guards. They will, in many polygons, not match. So here we have lower bound of 2, we have an upper bound of 2, so we know we're optimal. But in general, this ratio can be arbitrarily bad. So if you look at something that we call a spike box, so you just have a set of line segments in the plane, and then you're building a bounding box around all the intersection and have small spikes around the tips, then you can only place one witness. So you can hide someone in one of the spikes, but as that visibility polygon will intersect all the others, no matter where you place anyone. So you can't hide another one, but for guarding that, you need to find the hitting set for all of these lines, segments. And so that the ratio can be arbitrarily bad, but it is a lower bound that we can use. People are interested in finding classes of polygons where that's actually the same, or where we can show that this ratio is only a constant, something like that. So what have people looked at? The first results were what we call so-called art gallery theorem. So those are statements for a specific class of polygons, X guards are always sufficient and sometimes necessary to guard any polygon with n vertices from this class. And so the very first result was Quartal, who showed that if we have a simple polygon with n vertices, then n over 3 rounded down are sometimes necessary and always sufficient. So how do we prove these? The sometimes necessary is just there exist polygons for which we need n over 3 rounded down. And so this bound was from Quartal, this called Quartal-Coombe. So you obviously have these triangular spikes. And what you can see is if you would place a witness at every top of the spikes, then again, they have pairwise disjoint visibility polygons, so they only span this small triangular structure. And so we need 1 per spike, and that's n over 3 rounded down. And then for the always sufficient, we have to find a way how we can place n over 3 rounded down many guards, such that we can always see the polygon. And so here, Quartal's proof was relatively long. And then a few years later, Steve Fisk came up with an easy proof that says, okay, we have a polygon, we triangulate the polygon, and then we 3-color this triangulation. And then we use the least frequently used color. By the Pigeonhole principle, that will be at most n over 3 rounded down many guards. And we also know that we see everything because we have 1 guard incident to each triangle, and so this guard will see that triangle. We see all the triangles. So these were the first results where people looked at many different classes of polygons. And then, of course, the kind of natural next thing is to look at the computational complexity. So we're given a specific polygon, can you compute the minimum number of guards that you need? And that was shown to be NP-hard for various different variants. So first, for point guard with holes. So what do we distinguish? We often distinguish point guards and vertex guards. Point guards can be located anywhere within the polygon, and vertex guards are restricted to be on the vertices of the polygon. And then the other distinction that we often have are simple polygons, so that those do not intersect them, so the boundary does not intersect itself, and we don't have holes. And then we look at polygons with holes. And so the very first hardness result was for point guards in polygons with holes. And then Lee and Lin showed hardness for vertex guard and simple polygons, and then Agarwal expanded that to point guards without holes. So all the different variants of the traditional algebraic problem are NP-hard. And then, of course, the next step that people looked at are algorithms, and that depends on the complexity. So what exact polygon class do we look at? And also we will look at some other things that we can vary. So that could be approximation algorithms, it could be efficient algorithms for optimal solution, for many instances, heuristics. That's something I at least have not looked at, but the other ones. And for very restricted classes of polygons, we can have polytime algorithms, but that's really rather rare for the algebraic problem. And then what we're also often interested in are some structural results about the visibility, the properties of specific visibility types in polygons. Okay, so that's a very classical algebraic problem so far. We're having this vision that mimics human vision, and we're just having some simple polygon or polygon with holes. So what do we mean if we talk about its variance? So generally, we can alter either the capabilities of the guards or the environment that we want to guard. And so there are lots of different versions. So again, I'm going to be a bit lazy and restrict to versions that I've worked on. So I do have some figures on that. And one thing that we'll visit later are so-called K-transmitters. So if we look at this original picture that we said we can't look through walls, can't look around walls, corners. For K-transmitters, we can look through a certain number of walls. So for a 2-transmitter, we're allowed to intersect the polygon into connected components. And so in this case, if our guard here wouldn't be a normal human guard, well, still 360-degree vision, but the vision type is human, and it would be a 2-transmitter, then this guard could actually see the entire polygon. And so this is usually motivated by having modems. So if you want to have a connection, then that might be possible through a certain number of walls, but at some point that will no longer be possible. You could also introduce something like fading. So currently, for normal guards, we say it doesn't matter how far the point that I see is, I will see it. So it could be 5 kilometers away, it doesn't matter, I see it. Of course, if we have light bulbs or the like, then the light will fade over distance, and that you could look at. So then in this case, if you place a light bulb with high intensity, one at the left-hand side of this polygon, then the line segment 2 points on the right is fine, but it would be too dark there. So what you would then do is you place lights and assign an energy, and you want to make sure that everything is sufficiently lit. And then you want to, instead of minimizing the number of guards, you want to minimize the total energy that you use to light your polygon. And we could also do something that's called a chromatic art gallery problem. So we're still having a polygon, and normally we want to find a minimum guard cover, right? So that in this case would be n/4 many guards. For chromatic, we're not allowed that any point in the polygon is seen by 2 guards of the same color. So if we would want to stick with these n/4, well, all the points in the center body of the polygons are seen by all of them, so we would have to assign a different color to all of them, and we would use n/4 colors. But for chromatic, we don't care about how many we use, so we can do way better. So what we would do here is we just use alternating colors for guards at the top of the spikes. We use 2 colors, and then we can use 1 more guard for the center body, and we would use 3 colors instead of the n/4. We have n/2 plus 1 guards, but way few colors. So there are these different capabilities of the guards that we can look at, and there are quite many more. But so this is one thing that we can alter. And the other thing that we could alter is the environment that we want to guard. So very traditional is several classes of polygons. So as we said, simple polygons or polygons with hold. Very often we also look at rectilinear polygons, or also abstract from polygons. So there's something that's called or what we call a 1.5D terrain. So you have an X monotone chain, and then you can say, well, either your guards should be located on the terrain, so you have mountain range, and you want to see everything. So here, everything that this turquoise point sees is highlighted in turquoise. Or you could also say, well, maybe I have some, I don't know, drones flying over, and I have a cap at how high they can fly, and then I want to guard this from an altitude line. So these are the usual things that we can alter for various variants. And again, people have looked at these kind of art gallery theorems, these upper lower bounds, or computational complexity, or algorithms for approximation or solving. And so we'll go a bit more into detail into one of these specific guard capabilities, and those are the K transmitters. So again, we can look through walls. And if we want to make that a bit more formal, then a point is to or K visible from another point if the direct line connection intersects the polygon in at most 2 or K connected components. And then in the same way that we define the visibility polygon, we can define what we call the 2 visibility region and the K visibility region. And instead of having a guard set, we can say we want to have a set of points such they together the 2 visibility regions cover the complete polygon. Then we call that a 2 transmitter cover, K transmitter cover. So these kind of things are analogies. What differs are properties. So if we have a visibility polygon by the traditional definition of visibility, then the visibility polygon is connected. However, if we have a 2 visibility region, then that can have order n connected components. So here we have a simple polygon, and if we look at this brown point P, then we have these, in this case, 5 connected components of the 2 visibility regions. So now it's split. So what have people done for K transmitters? They've also looked at these art gallery theorems. So for example, I showed that I presented bounds for monotone and monotone orthogonal polygons. So again, very specific classes. Benninger and al. Looked at having not even any kind of polygon, but you just have line segments in the plane, and then you're trying to monitor the entire plane in the presence of these line segments. And they also presented a lower bound of n/6 to transmitters to cover simple n-gon. So as we saw before, there's this lower bound of n/3 rounded down for normal guards, which are 0 transmitters, we can't see through any walls. And here, the lower bound was n/6. And then what we did in 2018, we looked at some edge 2 transmitters, so where we can have a complete edge as a 2 transmitter, and looked at upper and lower bounds. We improved this lower bound to n/5, and that's the currently best known. So that's a construction on the right-hand side. If you look at the tip of these spikies, this is the A, then it can exactly see 5 vertices, and only from this shaded area it can be seen. So if you place the entire other construction below these lines and you place them around a body, then you get an n/5. And the somewhat interesting thing is that the best upper known bound is still n/3. So that comes from 0 transmitters. And of course, the 2 transmitters are way more powerful, but you somehow need to use the non-locality. So if you have these interlacing polygons, then you can always see into parts of a polygon that can, if you measure distance within the polygon, can be very far away, or can have a very high linked distance to what you can.
So yeah. Edge 2 transmitters, again, what is the definition? Everything that's visible from any point on the edge, or?
Exactly. So if you can be anywhere on the edge, so usually what we have, we'll look at some of them. So you usually have either these point guards that can be at point of vertices, then you have edges that are seen from any edge, then you have diagonals in the polygon, so anything that's seen from a diagonal, and then you have, we look at that sliding something, so you can place a line segment somewhere in the polygon and anything that's seen from that line segment. So those are the not completely stationary as point guards, but not as we see for Watchman route, where you really can be mobile and walk around. And so edge 2 transmitters are, you can see anything that is visible from the complete edge, or from any point on the edge. And then, of course, you can again look at the optimization problem, and not very surprisingly, as the outgrid problem is hard, all these different variants are hard. So even 0.2 transmitters for orthogonal polygons, minimum 2 transmitter cover is hard. Then people looked a bit at some kind of moving, and so what they call that are sliding K transmitters. So if you look at the polygon at the right there, and you look at this red segments, then what you can see is, if you would have a K transmitter standing on the line, but looking only orthogonally to that line segment. So all of that would be visible. If this would be a 4 transmitter, then this dark red is what it could see. And so again, this can be disconnected. And so the idea is you have a K transmitter that slides along a line segment, and you can only see in the orthogonal directions. And so there, people have either looked at minimizing the total length of the K transmitters that you place in the polygon to see everything. Again, that's NP hard, and people have presented the 2 approximation, and Bahu et al., Biedel et al., they looked at minimizing the number of sliding K transmitters. So placing one sliding K transmitter, no matter how long, always costs you 1. And again, that's NP hard, and here it's already NP hard if you have 0 transmitters. So but you can't look through walls, and if all of them are restricted to be horizontal. And also there, Biedel et al. Presented a constant factor approximation. And then what people have looked at rather recently is the computation of K visibility region. So how efficient can I compute what's no longer the visibility polygon, but the K visibility region. And Bahu was different set of authors looked at computation in limited workspace model and presented a general polytime algorithm, polynomial in the number of vertices of the polygon and the k. Yeah.
The 2 approximation is for k equals 2 or for general k?
I think that was for general k. Yeah.
For general k. Okay.
So that's kind of the furthest, the sliding k transmitter, the furthest mobility that people looked at for k transmitters.
And this is also for orthogonal polygons, or
no? So only this proof by Biedel et al. The hardness that is even restricted to orthogonal polygons was held, but the others is defined for general polygons and different types of. So you're not restricted to only have horizontal sliding k transmitters.
I was wondering if there is a variant in which more than one type of transmitters are allowed. So, for example, I may have a polygon in which a big k transmitter is an overkill in one part of the polygon, but not in the other, and so on.
No, not that I'm aware of. So what we are hopefully soon starting to look at was to look at a trade-off. So to look at, on the one hand, very high values of k, and then you need only few, or you look at lowers of k and you need more. So trying to figure out what the trade-off between k and the number is there. But I have not seen anything where people looked at different values of k to be placed somewhere in the polygon.
You mentioned the modem as a modem allocation problem, as a motivation, and I was just wondering is whether I need to allocate such strong modems at every corner, or I can have some discounts in other parts, and so on.
Yeah, you probably can, because I mean it depends a bit on, well, also how interlaced your polygon is. So if from any point you maybe can see into, so if you have a star-shaped thing, then you don't need a lot of power. But if you have a lot of this interlacing, you probably need some more power. But so I do think that there will probably be a good idea of using less power in some areas of the polygon. But yeah, I haven't seen anything, and I can't tell you off the top of my head either how that should look like. So I think it's a good idea, but I haven't seen anything about it.
Thank you.
Other questions? Okay, then we move a bit to more mobility. So far the guards were essentially stationary, or they were restricted to some line segments, edges, or these sliding k transmitters. For the watchman route problem, you have a single guard, which we then call watchman, because it's patrolling, and that can move. And so you're given a polygon, and then you want to find the shortest tour for a watchman, such that if someone patrols along the route, all points of the polygon become visible. And so here that would look like something like that. This pink structure would be the shortest watchman point. And what distinguishes this from the art gallery problem is that if you have a simple polygon, computing a watchman route can be done in polynomial time. And both affairs, so people started with having a starting point on the boundary and then computing that. But even if you don't have any starting point given, you can still compute that in polynomial time in simple polygons, while the art gallery problem in simple polygons is NP-hard. And then if we're going to polygons with holes, then also the watchman route problem is NP-hard. And one thing that's very central to computing watchman routes for normal guards, or normal visibility again, is what we call extensions. So extensions are just, you're extending edges of the polygon, and then any such cut will partition a polygon into two subpolygons. And we usually look at these with respect to a starting point. And what we can say is that a cut dominates another. So in this case, C1 will dominate C2. Why? Well, if you go from S to any point on C1, you will automatically also cross C2. So essentially you can ignore C2 because if you go to C1, you will have covered it automatically. And these extensions are important because, well, if you reach that cut, then you can suddenly see the complete edge. And so what we're really interested in are essential cuts, which are the ones that are not dominated by any other. And for these Watchman route problems, what you really have, so if you want to solve them, you need, or approximate them, if you have polygons with holes, you need to make sure that you visit all these extensions. And if you do that in a good way, then you, well, either you get a polytime algorithm or you get a good approximation for polygons with holes. And so this is something that we should have in mind, because later if we now look at not having a normal type of visibility, but if our Watchman is starting to be a K-transmitter, then this concept will suddenly disappear. And that makes it harder to come up with good solutions. And yes, in the same way as for the Adger problem, again, we can alter the capabilities of the Watchman, and we can alter the area that we want to guard, and then have lots of different variants here. So I'll go into a few details into K-transmitter Watchman routes, which is joint work with Bengt Nielsen from Malmö University. We presented at Qualcomm, and you can find an archive version if you want. So what's the idea now? We have a mobile K-transmitter, so we can have, well, essentially look through K-walls. And what we want is we want to establish a connection either with all points of a polygon or with a discrete subset. So again, if you want to have a motivation, think of, you need to drive around and there are certain points in the polygon that generate some data, and you want to get that uploaded to whatever central vehicle you have driving around there. And that could be just a discrete subset, or you have to do that for all the points in the polygon. And again, you want to find the shortest tour that sees all of these discrete points or all of the polygon and moves within the polygon. And you can define that without or with a given starting point. So either I say, hey, you need to start your tour here, or you want to find the shortest one, but you don't know what is a good place to start. And so this, having the small SSS, we look at the version with a starting point. And so the important part is that the extension do not translate to K-transmitters. So again, similar picture to before, in this turquoise point, we have this order n connected component of the two visibility regions. So essentially you can go to any tip of the spikes and you will see it. So it's not, once you covered an extension, you know, okay, you will see that complete edge. Here you could visit to see just this point, any of these connected components. And also if you would slide the turquoise point along an edge, it would differ. So essentially this one line would rotate around this vertex. So it's not the same. There's not one extension that you need to visit, and then you will see a complete edge of the polygon. And so we're really losing this locality that we had for a zero transmitter. And also, if we have a simple polygon, it's not even enough to see the boundary. So if you have this pink tour, and if you look at these 4 pink vertices or points along that tour, from that you see the boundary of that central rectangle, so which I try to highlight in red here. But there's no point along that tour from which you see the turquoise point. And it's a bit like what you have in guarding in simple polygons already. So this is what we call in CG Gottfried's favorite polygon. That's by Gottfried Toussaint. And what you can see here, if you place a guard at each of these yellow spike tops, then you can monitor the entire boundary, but you don't see the interior. And you don't have that for simple polygons and normal visibility, zero transmitters. But as soon as you go to 2 transmitters, you again have that even if you see the complete boundary, you will not see all of the interior. Okay, Okay, so with that, I'll move a bit into what we actually did. So what we showed in the paper are two things. One is an inapproximability result, and then we present an approximation algorithm. And so this one is the inapproximability. So we can't approximate to within a logarithmic factor. For the case, so we start for the case without a starting point and a discrete set of points within our polygon. And the reduction is from set cover. So let's say we have our set cover instances, universe U and collection of set C, and we build the bipartite graph on those, where we have the subset property on these edges. And then we construct a polygon where S, so the set of points that we need to get to C at some point, are all the elements of our universe and one additional vertex V. And so if you look now at the points representing our collection of sets C, they are at the tip of spikes that are connected to the upper part of the polygon. And then at this lower body, you have a lot of these T-shaped things so that you really can only see through the edges to the points, to the green points. And with the point V, we make sure if you want to see that, you need to visit its visibility polygon, which is in this snake figure there, or structure. And so you need to somehow visit that. And then if you make this corridor on the right-hand side very long, then you cannot afford to go to this bottom part where you would also see all green points. So you really need to visit the spikes. And then you would have to find the shortest one to find the minimum number of the spikes that you need to visit. And so that's reduction from set cover. And that actually also holds if we're giving a starting point. Why? Seems to be frozen. Okay, some of my mouse disappeared. I'll try to find it back. Now, okay, and so this holds even for the case with a starting point, because essentially you can place a starting point somewhere within the visibility polygon of our point V, and then again we need to visit the tips of the spikes and shouldn't move down this very long polygonal path. So this is already for simple polygons, while again, as a reminder, if we have normal visibility, then in simple polygons, we can solve the problem optimally. And here we have inapproximability result. Okay, so then
this is only for guarding a given set of points inside a polygon?
Yeah, but I mean, then guarding all of the polygon is not easier. So it's just a special case.
Okay.
Other questions? Okay, so what we'll do is we'll have an approximation algorithm. So we'll create a round R that approximates the optimum to this factor log square cardinality Sn log cardinality Sn log squared and so on. So where cardinality S is again the number of discrete points to which we need to establish a visibility connection, and N is the number of vertices of our polygon. So I'll try to give you an idea how we do that. So what we do is for each point in S, we have different connected components, again, up to order N, and we need to visit one of them for each of the points in S. So what we do is we create a candidate point for each connected component of the K visibility region for each point in S. And these are the intersection of geodesics from the starting point to the cuts. Okay, so what is a cut? Here we have a point S1, and we have two connected components of the K visibility region, and if we introduce a starting point S, then we have one window, so an edge of a connected component of the K visibility region that is not an edge of the, or a subset of an edge of the polygon. So here these two would be our cuts, and these are the ones that any path from S to any point to that connected component needs to cross. And so we'll look at the intersection of geodesics from our starting points to all of these cuts. So let's look at a slightly larger example. Here we have our set S contains 3 points, S1 in blue, S2 in red, S3 in green, and our starting point S is in white. And so we see, for example, that the 2 visibility region of S1 has 6 connected components, which are all indicated in blue in that figure. And all the cuts to the different connected components of the 2 visibility regions of these 3 points are always indicated in turquoise. And so now we compute the geodesics from S to all of these cuts. And those are candidates points, and we actually introduce one more set. We just have one representative per cut. And now, first on these darker pink points, we build a complete graph. And the edges between any pair of pink vertices is just the length of the geodesic between these 2 pink points, where again, a pink point is defined by the point where the geodesic from S hits that cut. And we add these light pink edges in the graph that you see on the right that have cost 0. And the idea is that if you visit a certain cut in a point Pij in one of these dark pink points, it might happen that on the way you're kind of getting for free other cuts because you pass them. So these will get for free, though they have length 0. So if you want to see an example, here on the right-hand side, if we visit the connected component K33, so the green point there, we also visit 2 other cuts. So we visit the cut of K15 and the cut of K21. So we get edges, and also, of course, the cut of K33 by definition. So we get these 3 edges of length 0. If we visit that cut, we get the other ones for free. And so what do we know? Our graph has n times s, or order n times s many vertices. And what we then do is we group these. So all the groups that belong, all the representative points that belong to the same point in our discrete set S. So all these that are on some of its cuts, either the dark pink or the light pink ones. So in here, and we add another group in which we just have our starting point. And so here we have in gamma 1 that are indicated in blue, all those that belong to S1, and gamma 2 that are red, those that belong to S2. Green are those belong to S3, and then gamma 0 is just S. And what do we do then? We approximate a group Steiner tree. So what's a group Steiner tree? We're given a graph with m vertices, and you have q vertex subsets, which are called groups. And the task is then to find a minimum cast subtree of the graph that contains at least one vertex from each group and minimizes the weight of the tree. And for that, Gark et al. Presented a log square m log m log q approximation. And so if we do that, well, what do we have? Our graph has order n times s many vertices, and we have, well, one group per point in S plus 1 for our starting point. So we have canary S plus 1 groups. And we'll approximate that group Steiner tree, then we double the tree and we have a route. And that has to be feasible because we visit one point per gamma I, and then per definition, we visit at least one cut of the K visibility region of each of our points. So then the only question is, why do we achieve the approximation factor that I claimed, that we would achieve. And so I'll go into, first, I'll try to give you a general proof idea, and then I show you some proofs of that, and hope I'll still manage that in time. So what do? We look at, we don't know the optimal route, but we now want to alter that to pass through the points or candidate points that we just created, these ping points, Pij, and we want to show that we can alter that, and that will only create a route of length at most constant time, the optimal route length. So what do? First, we look at all the cuts of the k-visibility, of the connected components of the k-visibility region of all the points. And so we call them C. And then we look at, well, which are the points where opt visit these cuts? And if it visits that a couple of times, we take where visit them the first time. And then we don't look at all the cuts C anymore, but only the essential ones. So again, reminder of essential cuts were the non-dominated ones. So if you pass another one, anyhow, if you move from S to an essential cut, the other ones get taken out. And now we keep on filtering our cuts. So we order the essential cuts that we have by the decreasing Euclidean length of the geodesic to these cuts. So G1 is the longest, the cut with the longest geodesic to it. And what we filter out is, we look at one and we check whether there are any other cuts with geodesics that are shorter to them that we intersect. If that is the case, we delete all the cuts from our set. So any geodesic that we're left with will not cut any other cut in the set that we're left with. So this is the set that we're ending with. So if you look at, again, at the example that we had before, then the light yellow ones are our central cuts. So the other ones are dominated. And actually, in that step now, we don't filter out anything, because if you look at the geodesics to any essential cut, we don't cross any other of the essential cuts. So here we don't filter out anything, but potentially we filter out, we would start with the longest one and see, does this geodesic already cut any of the other essential cuts? And then the first claim, so the claims are the things that we still have to prove, is that the geodesics that we're left with are independent geodesics. So no essential cut is visited by two of these geodesics. The second claim is that each essential cut that's visited by the optimum, so that's in C prime in the second set that we had, is touched by exactly one of the geodesics. So touch means it's either intersected or actually we're only getting there. And the geodesics have to intersect these cuts in the points of the type Pij, so the ones that we defined as candidate points for our graph, because that's exactly where geodesics intersect with our cuts. What we do then is we build the relative convex hull, so the convex hull with respect to the polygon that's inside the polygon of all the points Oj, where the optimum visits all our cuts, and the points that we're left with on our filtered out cut set of the Pij. And then we call that relative convex hull with respect to P. So what can we say? If we look at this relative convex hulls of the points of opt and the Pij points on the cuts that we're left with, then no geodesic will ever intersect between the point where opt visits and our candidate point on the same cut. And so if we have a pair of these points of the type Oj prime Oj on the optimal route, we can have at most 2 points of our point of the Pij that we're left with on this relative convex hull. And so we can use that to show that the relative convex hull of opt and our points has lengths at most 3 times opt. So rerouting opt to go through our points only costs us a constant factor. And again, my mouse disappeared. No. Then the last thing is, again, relatively easy. Of course, the relative convex hull of just our points is not longer than that of our points plus the optimum. We also know that the convex hull of these points, or we show that of the points that we're left with it 1 point per group, except for possibly our starting point. And so if we put that together, we might need to pay another opt to connect what we have to the starting point. And then if we puzzle all of these together, we get constant time, this logarithmic factor from Garg et al. Times the opt. The things that we need to show are all of these claims, and I'm not going to do all of them. I'll just do one very easy one and one that has a few more geometric insight, and then we'll finish off. So the first claim was that what we're left with after this filtering out are independent geodesics. So no eccentric cut is visited by two of these. Why? Well, we just ordered them by decreasing lengths, and then we start with the longest one. So whenever our current geodesic intersects any other cuts in our set, we deleted the shorter geodesics. And so then, by definition, after the last iteration, no two remaining geodesic with it the same essential cuts. So that was relatively easy from filtering out. And so, as I said, I'm going to ignore claim 2 for now. What I try to show is that this relative convex hull has lengths at most 3 times the opt, so we can somehow alter the opt to go via our candidate points. And so we start with the first thing, the first statement, that between a point the optimum visits and a point of our candidates, there can't be a geodesic that intersect that. So let's say we have a cut after filtering out, that's from connected component J of the K visibility region for the point Si. And now we have between Oj and the point Pij both are on the convex hull. And now we want to say that no geodesic intersects between those two. So why is that true? Let's assume we have one. So it's a geodesic that has to go to another cut. So let's say it goes to cut C prime, and it has to cut between Oj and Pij. And okay, then it has to intersect C in some point. So let's say it does so in point PC. We have different cases. So either the length of the geodesic to C prime is longer than that of C. Well, in that case, we would have deleted the geodesic GC in our deletion procedure whenever we intersect other cuts. So then this wouldn't even be in our set, and well, that case can't happen. If the geodesic to C prime is shorter to that of C, well, that can't happen either, because if now the geodesic to C prime restricted until the point where it actually intersects our cut would be shorter. And that's a contradiction to that we started out with geodesics, so can't happen either. And the only case that we have is that they're actually the same. And then either, again, the restricted part to just the intersection point is the same, or they actually, our candidate point and the intersection point are exactly the same point. And again, we're good in that case. Okay, so that showed the very first part. Now, what we want to say is that if we look at 2 points that the optimum visit on this relative convex hull, we can have at most 2 points of our pink candidate points on the relative convex hull. So how do we show that? Let's say we have 2 of these consecutive points, Oj, Oi prime, J prime. And so what we know is there could be 2, the Pij and Pij prime can be between them. So if you look at the lower right-hand side there, you have in blue the point that op visits, in pink our candidate points. It's where the geodesics that you see in pink hit our cuts, and that the turquoise one are the cuts that we visit. And so we visit OIJ and then OI prime J prime. And now what we assume is that we have another point. Well, what we know by the first part here is that between OIJ and PIJ and OIJ prime and PIJ prime, there can't be another point. So the point that we would want to have has to be between the two pink points. So another pink point has to be between the pink points intersecting. So this is this P kappa lambda that I inserted there. And so we assume that this is on another cut, let's say C double prime. So what do we know? Well, opt has to somehow visit that cut as well in a point, okay, kappa lambda. But we know that this one has to happen either before both OIJ and OI prime J prime or after, because these are two consecutive points of the optimum. So what we do here in this example is we can, without loss of generality, assume that's just after it. And what else do we know? We know our cut is a line segment C double prime. So let's now look at this red polygon. So it's defined by the points OIJ, PIJ, P kappa lambda, O kappa lambda, OI prime J prime, and OIJ. Then what we know is that the point Pi prime J prime is in the polygon's interior. But we started off with assuming that this has to be a point on the relative convex hull, but that can't be the case because the other points are on the relative convex hull. So that could not have been on the relative convex hull to start off with. So we know that between any two pairs, any pair of points of the optimum, we can have on the relative convex hull, we can have at most 2 points of our candidates. And then we can use that to get our factor of 3. So we know that we only have 2 points. So here this Pij and Pi prime J prime, and we look at where the geodesic to these points intersect our optimal route. So these in this row Ij, so the yellow points, is where the geodesics cut the opt. Yeah, just a lot of claims. We know that we have a geodesic. So going from rho Ij to Pij has to be shorter than going from rho Ij to Oij. Otherwise, this wouldn't be the geodesic, wouldn't be shortest. So what we know is we can make a bit of a detour here. So we go from Oij, instead of going from Oij directly to Oi prime J prime, we interrupt at the yellow point, make a slight detour to pink, and do the same from the other yellow, make a detour to pink and go back. That can be at most 3 times the length of a section between those, again, because pink is the geodesic. And so this tour, that rerouted tour, has length at most 3 times opt. And we know that the relative convex hull is the shortest of all tours that visits the blue and the pink points. So it's at least as long as this rerouted one that has the same visiting property. And so we know that our relative convex hull is at most 3 times the length of the optimum. And so there are some more details, but if we put all of that together, we know that we can alter the opt and only lose a constant. And with that, again, we get our slightly strange approximation factor for the K-Transmitter-Watchman rod problem. So let's finish with a brief outlook. The obvious question would, of course, be if we don't have a given starting point, or if we should monitor all of P, can we get any useful approximation? And something that, at least if we want to monitor all of P, we probably need some kind of structural analog for the extension of the Eurotransmitters. So currently we have no idea what we need to visit if we don't have a discrete set of points. And to do that, we need something better. And the other thing, what I briefly mentioned, is that the best upper bound on these kind of Art-Garris theorems still stems from zero transmitters, so that n over 3 rounded down 2 transmitters are always sufficient. And this has been interestingly difficult. So many people have looked at that. At some point, we managed to get an n-1/3 rounded down, which is not really interesting. So anything that eats off of that upper bound and actually uses the two transmitter properties is really interesting to find. And with that, I would say thank you for your attention, and I'm happy to answer some more questions.
Thank you. So I have one question. Can this be extended to more than one watchman? I mean, using the same technique?
Not using the same technique, because so what we're currently using is this group Steiner tree, and that just has one tree. If we would have several, we would have to define which watchman. So if we want to use also the Steiner group, which watchman should visit the extensions of which point. And if we don't define that, then we can't use exactly that.
Okay. And do you think it is possible to extend it to guarding the boundary, or
to guarding just the boundary?
Yes.
I
mean,
no, I don't see that, because it's kind of the same problem as if you would guard the interior, because you still don't know. There's not one line segment that you need to visit, and you suddenly will see a complete edge. You could see an edge from very different parts of the polygon, for example. And
but you could make it like if you want to guard at least 1 point from each edge, then I guess it's similar, right? Just extend the visibility polygon from each edge, and then
that would work. But if you need to see the complete edge, then no idea. So I think that also still needs this some kind of extension. It won't be extensions, but some kind of structural idea. What is it that we need to visit to see everything?
Maybe some discretization of each edge. Okay, maybe it's something to think about.
Yeah, we can meet to think about it.
Question. Maybe I missed something, but you said that you are using Steiner tree, and if I'm not mistaken, solving a Steiner tree is NP hard. So
no, well, yeah. So what we're using is a group Steiner tree, and it's an approximation to a group Steiner tree. Let's go to the right slide.
To solve that, do you need to use linear programming, or is it done in a different way?
It's done doing a different way, and it's only an approximation. So we don't solve the group Steiner tree, we approximate the group Steiner tree, and the approximation ratio is for just that is this order log square m log m log q, where m is the number of vertices in the graph and q is the number of groups that we have, where we need to visit one vertex per group.
I see. Thank you.
More questions?
Adding more dimensions, like 3 dimensions, like many dimensions, how complicates it the things?
Okay, so the art gallery problem, not so surprisingly, remains hard. And so if you, in the beginning, I introduced some variants. Where do I have that here? So even this terrain guarding, if you have just a X monotone chain, and you have to place your guards on the chain, then this is still NP hard. And of course, it's also still hard if we have something that we call a 2.5D terrain. So where you have you take points in the plane and you lift them to different heights, and that's what we tend to call the 2.5D. Those are still hard. Strangely enough, if you do that from an altitude line, then suddenly it's very easy and you have a polytime algorithm. But most of the things are hard already in these very low dimensions, and adding dimensions is not really help.
Really,
There
you have
are
a
some
exact algorithm for surfaces, like exact algorithm?
for guarding a 1.5D terrain from an altitude line. Yeah, it's the same as having what we call a mountain polygon. So where you have one line and you have kind of a histogram. It's just not a.
But
it's just an X monotone chain.
What we call weakly visible polygons. We have 1%.
Yeah, but that's.
But
But that's harder.
really?
Yeah.
Okay.
So it's really just one line, and if every point on the upper polygonal chain has, well, you can just go straight down and you hit this one line, then everything gets easy. You can just make a sweep over the line, and and you can show that it's optimal, because here you can actually find a matching set of witnesses. So you have a matching upper and lower bound, so you can show that it's optimal.
Right.
Okay, and maybe another question. I'm sure that I can explain what I think about. You are talking about visible and not visible. If we had aspect of quality, are we staying in the same problem, or this is like completely different problem? I want to cover everything at minimum, at specific quality, or I need to cover some part with high quality, but I can leave other part with lower, small part, lower quality.
So there are some variants that go into that direction. So one is where you need to make sure that, for example, each point is seen by at least 2 guards. If you want to see something about quality, so say, well, some can stop working. And on the other hand, if you go, I did mention briefly that we've also worked on exact algorithms. So essentially what we have is a primal dual approach, and you can separate efficiently because it's just an overlay of visibility polygons that you have there. And that, of course, you can alter in any way that you want, that you say, well, here it needs to be covered really well, and here maybe not. And then this could again depend if you have something like fading, where you can use the same thing. Then you can say, well, maybe some areas here, well, they shouldn't be completely dark, but if they get some energy, then that works again. But in all of these things, I only know about exact, so it's mostly about exact algorithms, and there are some, at least for fading, there are pieces for the vertex version, so where you are restricted to be on vertices, and there I don't see that you need to have this constraint that everything has to be 1, so you could alter that and that should still result in a p-test, but I don't know any other restrictions on quality. So it's usually about either being seen by more guards or having guards in a certain distance or something like that, that quality restrictions are then what we have.
Okay, thank you very much.
Welcome. And again,
okay.
Thanks again.
Thank you so much.
Thank you very much.
Thanks. And
Yeah, you got
Thank
you. Beautiful slides, Christiane.
thanks. Bye.
Bye bye.
Bye-bye.
Thank you. Bye bye.